All right, everybody, let's go ahead and quiet down. Thank you for joining us. We're going to go ahead and get a discussion started about covert hardware implants with Matthew and Jonathan.
Yep.
Awesome. Thank you guys, everybody.
All right. Thanks, everybody. Can I get a show of hands? How many people here have heard of hardware implants before? Think Croc, rubber ducky, OMG Cable, right? So most people. All right. Now leave your hand up if you have heard of inject on hide or hide and seek. We got a couple. All right. Great. How many of you have used those in a real world op before? Yeah. See. All right. We're hoping to change that today. So with that, let's go ahead and jump in. Welcome to Hide and Seek. Who owns your keyboard? My name is Jonathan Fischer, and this is Matthew Richard. A little bit about ourselves. I've been in the InfoSec community now about 8 years. All that's been on the offensive side of things. Prior to joining InfoSec, I spent about a decade designing, implementing, and programming electrical control systems. Now, this was for primarily off-highway machinery. So I did a lot of radio controls, a lot of human-machine interfaces, and a lot of just embedded design. And I did some factory automation as well. But that ultimately led me to start identifying gaps in security in that industry, which led to my transition over. Since then, I used my experience to create the Inject on High platform with my buddy and coworker at the time, Jeremy Miller. And we've talked about that now a few times since.
And I'm Matthew Richard. I'm a software developer. I've been working for about 5 years. I'm really into embedded hardware, so that's kind of how I got into this. And recently I became an Inject on Hide contributor to this project. So turn that back over to John.
All right, so standard work disclaimer. Everything you see in here today is that of is our own and not that of our current and previous employers. And now that we got that out of the way, let's go ahead and catch everybody up. So 2020 comes around, and I'm talking to Jeremy. And Jeremy and I both want to highlight, some of the things we've seen with hit implants, as well as supply chain issues. And we're sitting around trying to figure out what the best way to do this is. So we came up with kind of a list of things that we wanted to address that we weren't currently seeing on the market. Now, one of these was the ability to custom fit. When a lot of these items are purchased, like think OMG Cable, Croc, USB rubber ducky, everybody can identify those, right? So they're getting harder to mask. People are getting more leery about putting a lightning cable into their computer. So they're doing their job. But we wanted to adapt for real world engagements. Another thing we wanted to look at was the ability to change things up a little bit. A lot of these were spinning up access points to communicate with, so we wanted to hide a little bit better. And we wanted to get off of the target network infrastructure to avoid more detections if we could. We were looking to exploit a different layer on the OSI model. And we also ran into a unique scenario where we were asking a lot of questions about what was going on in the hardware, what were you doing with our data? Because we were handling PHI and PII, we didn't want to lose control of that data through somebody else's network and just take their word that they weren't siphoning it off or that they weren't protecting it, right? So we wanted to try to find a way where we could control that ourselves end to end. And finally, we wanted to take this to an enterprise level threat. One device could hit a targeted target and maybe get the information you want. But if you have a large enterprise, you might not get that one target. So what if you could do 100 of these? What if you could do 1,000 of these? Now you start getting to those numbers that make sense for a large enterprise. So I'm happy to report in 2021, we built it and we met our goals. But the problem is in 2021, we had COVID. So we decided to roll the dice because we did not think this would make an impact being released on video at DEF CON or any other conference where nobody could actually see it work. So we sat on it for a year, hoping and praying nobody else beat us to the punch. And thankfully, nobody did, and we were still able to release our research then in 2022 at Hacker Summer Camp. So we did a talk at B-Sides Las Vegas, the demo labs at DEF CON, and the board design talk at Hardware Hacking Village. And this is ultimately what we have. You'll see the basic attack flow here. The keyboard attaches to the implant then connects to the computer. And we have onboard storage with an SD card and a wireless interface out to a C2. So nothing overly complex from a attack flow standpoint. Now, when we released it, we had a vendor on board. This was big for us because during the time we had the chip shortage, and the vendor gave us 50 boards to hand out. Now, some of you maybe have gotten those boards, but regardless, after DEF CON, when we were going to put this up for sale, the vendor closed up shop and ghosted us. So we had to redesign the board, which is the board you see here. Now, when I did that, I took standard components from JLC PCB so that we could just upload the files and get a 90% completed board. If you look at the board, you'll see a USB in, you'll see a USB out, you'll see that micro SD card there, and a Digi radio for our interface. If you look on the left, you'll see 2 microchips. Those are SAMD21 chips. Those allow us to interface with USB in and out, and then we have the 2 programming ports there. Now, those programming ports are primarily the components that are hard to source through JLC PCB, but we'll address that in a little bit. So that's what it looks like. But what's it do? Well, we do what you hope we could do with a device that sits in between keystrokes and a computer. We can sniff the keystrokes, we can record them, we can mangle them, we can inject them. And when our device mounts, we mount as a generic HID device. So that means not only can we do keystrokes, but we can do mouse movements as well. So we can do a mouse jiggler. We renamed it Insomnia mode because I just hate saying mouse jiggler and typing it over and over. So Insomnia mode. Now we do it a little bit differently than some. We move the mouse out 1 pixel and back every scan cycle. So what we're doing here is we're preventing the computer from sleeping while avoiding the mouse drift and the visible movement because it's only 1 pixel. Easy to detect if you're looking for it, but you can go into the source code and randomize the movements and randomize the timing. You can even add things like, F13 through F24. The keys that you don't find on most keywords anymore, but still exist, right? It's open source, so feel free. But getting back to the standard features, we can also do a remote status check. Because these are USB powered, we don't know if they've been unplugged in the field or not. So we have the ability to talk to them, see what's going on with them, see what's active, and then we can interact with the file system as well. We can push scripts, we can pull down data, we can delete data at will. So kind of what you'd hope, right? Well, we set out to be a little different. So what did we do differently? Well, we not only mount as a standard HID device, we also mount a side channel. And we'll cover that in a little bit, but that's one of the key features to some of what we're doing here. We decided to get our scalability through our network, so we came up with a scalable covert network as well. And in doing this, we came across a set of radios that we found a way to make field swappable. So if you wanted to change your RF footprint and environment, you could switch from 2.4 gigahertz to sub-gigahertz or change radio technologies on the fly, which helps us avoid war walking or things of that nature. Or if we just want to utilize different technologies, we don't have to have completely different boards. And then we have the ability to remote wipe and go into a self-destruct mode, if you will. Now, the point of this mode is if I'm going to leave the implant for a long period of time, I don't want to leave the keystrokes I captured or my injection scripts laying around, so I can delete it all. And then we also go into a passive state. So when we deploy our implant, we wait for a key command to wake up. So we won't respond to replays or anything like that until we receive that command, because we want to keep that RF noise as low as possible. So that covert scalable network, let's talk a little bit more about that. Well, if we're controlling the data, we have to ensure we have authentication and encryption involved, and we're able to achieve that through our radios. All the radios we use have the AES-256 encryption implemented. But more importantly, scalability. Now, when we think of scalability, mesh network just comes to mind. And honestly, when we were making this, I was surprised more people weren't utilizing this. Because it's mesh, we are actually encouraged to drop more devices. So not just one device, but we use the Digi international radio called the XB. Now, the XB has a protocol called DigiMesh, which is proprietary to them, but it's a lot like Zigbee. And with DigiMesh, you can actually drop 999 implants with one C2 without even changing the network architecture. So it's pretty much set and forget and you're encouraged to do more. And because it's mesh and we're bringing our own network, this means we can start jumping air gap systems. We can change the shape of our network to go around barriers that might impede our signal. We can jump building to building if you want. You know, if you want to go James Bond or Mission Impossible, put one on a drone, you know, go all the way down to the coffee shop down the road. But you have the ability to do that. Ranges. So published ranges are these. You have a minimum of 200, 330 for the Pro version, which is what we're using, all the way up to 2 miles. Now, I'm using USB power, so I'm going to be on the lower end in a noisy environment with lots of obstacles. But even this, 300 feet in an office complex is a long way away, right? So that gives me plenty of opportunity to drop another repeater or another implant to start getting the range out. For a real world test, I put one in my basement and one in my garage, and I was able to get a full city block away with just 3 radios, 2 implants and a C2. So when I say go down to the coffee shop and do this, it's actually a reality. And finally, if you have a 999 implants, you don't want to talk to them individually. So we do have the ability to do a global broadcast or unicast message as well. All right. So that's what we released, but let's go ahead and show you what that looks like. Well, let me get up presenter mode once. All right. So if we go to our C2 folder, you'll see 3 scripts. The first is the C2 script. It's written in Python 3, nothing crazy. The other 2 are keyboard parsing scripts, which will come into play later. We just go to our command terminal here and just launch our C2. We'll be greeted with a banner as well as the screen for our COM port. Let's go ahead and pick the COM port. For the radio, we'll choose the baud rate and the radio interface, which is the XB. All right, so now let's step through this like this was real world op, all right? The first thing I'm going to do in a real world op is I'm going to scan for implants, which is my option number 2. And the reason we do this is we don't know what got unplugged, what's powered, what isn't, what failed. So we want a real list every time we engage. So we're going to take 10 seconds, look through the environment for what implants exist and feed that back. All right, so here we have an implant named implant with a unique identifier there. If we go over to the folder, you'll see we have a new file, xb nodes.txt. If we open that, you see the same information with a timestamp. So you get an idea of when this was scanned last. But more importantly, we refer back to this file when we build out your target list so that every time you scan, you get a dynamic change in your menu. So you don't have to remember these IDs. You can just select your target. All right. So going back, we know we have a target. What else can we do? Well, we have a target. Let's see if we can talk to it. So we'll get the implant information with number 4. And here you're going to see, oops, sorry. We need to wake it up first. Remember, we're in that passive state, so we're not responding. So we'll activate the implant first. And now we'll get that information. And it's going to come back with 3 modes. We're going to have key recorder mode, which is deactivated. We're going to have insomnia mode, which is mouse jiggler, which I don't have active either. And we're going to have last key press. Now, I don't know how many people do this, but we figured we have the data, so why not? So we record the time since we were powered up or the last time we saw a key press. And this is going to help us determine when we want to inject scripts. If it's been 1 second since the last key press, it's active. Somebody's going to notice. If it's been an hour, the computer's probably asleep. 2 days, you might not even be plugged in to a computer anymore. 5 minutes, maybe you have a good window to start doing some injection attacks. But you get an idea of how active your target is at least. And more importantly, right now, we know we can talk. So looking back at our list, we have the next thing down, which would be sniff keystrokes live. So we'll go ahead and do that. We'll choose our target. And now let's go ahead and type. So how about just CactusCon? If I hold shift and I type in cactus, and I'll give it a space to show that. How good it is. All right. Con, and I'll give it an exclamation. And I'll even hit escape so you can see us tracking it. So you're echoing it live on your screen as it's passing through. Now, some things to note here. We have to make some assumptions with these keystrokes. We're assuming they're US keyboard encoded because we're translating them for you on the screen. So that's what you're seeing here. If we jump back over to our folder again, you'll see we have a new file. That unique identifier -live keys txt. If we open that up, you get the timestamp from when you started and when you stopped your scan. You also get those letters coming in. Again, we're assuming US keyboard encoding. It's open source, so you can change that mapping if that's not what you're expecting to use. But another thing to note here, if you start and stop this multiple times, we just keep it pending. We don't overwrite the file, so you can keep track of all that. But realistically, if you're doing this in engagement, you're not watching one computer. So this is more useful for profiling, seeing what's going on. Am I interacting with a dev? Am I interacting with an admin? Or who am I looking at and what are they doing, right? Is it even worth recording their keystrokes? If it is, you're more likely to use the next option here, which is enable keystroke recording, which is option number 8 right here. So if we do option 8, and for sanity's sake and demo gods, because we made no sacrifices, we are going to check. Now we're going to go ahead and see key recorder mode's active and insomnia mode's deactivated, and it's only been 24 seconds since the last key press. Now if I go ahead and clear the screen, those of you in back probably can't see this, but that's okay. You can take my word for it, right? All right, so now we'll do something like, how about just red team? And we'll give it a question mark this time. And let's hope I spelled that right. I guess we'll find out. All right. Now we'll go ahead and look at our menu again, disable it with option number 9. And we'll clear the screen. And we'll just ensure that we killed that mode. Again, you don't have to do this. This is for sanity's sake and just prove that we deactivated it. All right. Now this time, if you go back, you'll notice we don't have any new files. Can anybody tell me why there is not a new file here? That's right. We're storing it locally. This is a set it and forget it. So in an engagement, what if I don't want to sit through second and third shift? What if I just want to set this and come back a week, right? So it's storing it on that SD card that we have there. So we have to actually grab it. For that, we'll use option number 10. Choose our target. And we're going to choose the keys.txt file. And now you get a whole bunch of dots because I cannot program an ASCII spinning wheel to save my life. So you're going to get dots and you're going to like it. All right. So dots it is. Now we have the new file. And now I'm going to grab the name. But in the file, you're going to see keystroke packets. Can anybody read this? I didn't think so. All right. Now, the reason we do this is we don't want to make assumptions at this point. I don't want to assume keyboard encoding. I don't want to apply logic to it. What if I'm wrong? I lose the integrity of that data. And if I've been recording keystrokes for 2 weeks, that would suck, right? So raw data. You can tell this is a keystroke packet. You have the K to start. The next byte is your modifier byte. Now, the modifier byte tells you what modifiers are pressed. So Alt, Shift, Function, things like that. The byte after that's reserved. You're not going to see any keys in that. And then you have 6 more bytes of data that tell you which individual key was pressed. So if you have 7 keys pressed, you're not going to see that 7th key, just the first 6. And that's the way the packets are transmitted. But not readable, at least not for me, not without a lot of practice. So those key parsing scripts I was telling you about when we started, let's go ahead and run those. We're going to start with verbose. So you give it the input name for the file, you give it an output file name. And now when you look at it, you see that keystroke packet. And then you see the translated value on the right. So this will help you troubleshoot your code as you fly, but it's not really useful, really, when you're trying to get your information. Now, if you're going all crazy on me and you want to feed this into an AI model to try to profile somebody based on their typing habits, by all means use this. But realistically, you're not pulling out the juicy bits here, right? So we have a second parsing script for that. and that is our output one. So we'll give it that same name again, and we'll give it an output name. Now this time, you'll see I was hitting backspace to clear the screen, and you'll see red team with a question mark, which is what I was typing. Now, I spelled it right, thankfully, because there's been a demo or two where I haven't, so. But that is what you hope to expect, right? We're talking about standard functionality from a keyboard implant. So we're kind of in the 7th inning stretch. Feel free, get up, stretch, hide the kids, because we're going to have some fun. Remember that side channel we're talking about? Let's go ahead and play with that. All right, so this is option 14, launch attack from script. So we push our injection scripts to be stored on the SD card so we don't have to transmit individual keystrokes. When we enumerate the scripts, we see we have 3. We have a hello world script, we have a stager script, and we have a COM shell script. So I'm going to go ahead and launch the COM shell, and I'm going to tell you what's happening as it goes. So we're using keystroke injection to spin up a PowerShell session. In this session, we are looking for that COM port that we are attaching. In that COM port, we are redirecting standard in and out, and then we minimize the session. So if you're following along, we now have a reverse shell through the COM port, but it doesn't stop there. Through the COM port, through the implant, out the mesh network to our C2. So now we have a COM shell that is controlled in our network existing outside of any network scanning and network protections, right? We now control that particular shell. But you don't see it here. And the reason is if we launch this on multiple devices, we can't connect to them all at once. And sometimes you just want to connect and reconnect. So for that, we're going to jump all the way down to option number 16 here and do our interactive PowerShell terminal. We're going to choose our implant, and once we attached, we are going to launch our super secret hacker command. Anybody know what that is? Nobody? All right, it starts with a W. Yeah, who am I? So we're going to wait a second, and we're going to see we're on the computer surface tension with a very self-aware user named Victim. Clearly, Victim has taken their cybersecurity training courses and is aware they suck. So, thank you, Victim. And because Victim sucks, we're going to go to their desktop where they probably stored some fun information. Once we're on the desktop, we're going to enumerate it. And now you're going to get my spiel. This is an IoT radio network, remember. We are prioritizing power consumption over speed. So we're moving slowly, but that isn't necessarily our enemy because we don't have to worry about network detections. We control the network. So we have the luxury of time here. As we wait, you'll see we have 2 files. We have black cell.txt and loot.txt. Those look great. Now I could enumerate them like you would in any other shell, but I want to go ahead and show off a little bit more because I'm up here and showing off is fun. So I'm going to do exit twice. It's PowerShell and demo gods and all. I'm going to make sure it actually exits. And I'm freeing up the COM port if you're wondering. This time, I'm going to go down to option number 13, where I'm going to receive a file from the victim through that COM port instead. Choose the implant. We're going to give it the path, see users. Thank you, victim, on their desktop. And we want loot.txt. What should we name it? Well, I think woot.txt sounds like a good name. So woot. This time, I'm not going to spam you with dots because that was a little excessive last time. I think we can all agree on that. So this time you're going to get little stars and dots. Oh, no. The timers are a little changed on this one so you can see the code injection. That was on purpose. You're going to have to change the timers on every device if you want. Everything reacts a little differently, but anyway, I digress. So stars and dots this time. And what we're doing with that PowerShell script is instead of redirecting standard in and out, we're finding that file. We are gzipping that file. We're base64 encoding that file. And then we're chunking that file to play nicely with our buffers, and then we're transmitting it over, and then we're reversing the entire process on the C2 where we recreate the file. So now if we jump over, we see that the file finished. We have woot.txt, formerly known as loot.txt. And here you can see we have our loot. I'm a dad, you get dad jokes, suck it up. I have a license. All right, so we have our ASCII loot. All right, so to recap, we just launched our reverse shell through a network we control through a side channel on the COM port. We also exfilled data through the COM port. Pretty freaking cool, right? Pretty cool, right? Yeah, all right, thank you. All right, so that's what we released in 2022. Now, we didn't stop there. We had a lot of feedback when we released this, mostly around, well, done with video, hold on, backup video, mostly around LoRa. Can you do LoRa? I like new technology, you like new technology, why not? Our European friends were very fond of LoRa. They made the most requests for it, so we made it. And we released it last year at Black Hat. Now, I like the name inject and hide, right? I think it's clever, it's fun, but so is Seek. So we decided to make some shields, and to make Seek work for a name, we came up with the name Shield Exploitation Expansion Kit, because you got to make the acronym work somehow, right? So shield expansions. On here, you'll find we came up with a couple expansions. On the top is a 998 RAX radio that does LoRa. And then we have LoRa WAN right below it with the RAX 993. Now, the reason we chose these are they're readily available on Amazon. And they also use the same UART connection that we were using with the XB radio. So it literally became plug and play for us because I designed the boards to work with that same through-hole mounting that XB had. So now we can change from DigiMesh to Zigbee, Zigbee to LoRa, LoRa to LoRa WAN, all with just swapping out modules. From the C2 side of things, we just select which radio interface we're using. From the implant side of the thing, the side of the house, we don't care because that implant only cares about the message coming in. And if it received a message, it has to be the right radio, right? So we fingerprint based on how that data is formatted. And when the implant sees it, it just locks into that formatting mode and communicates instantly. So all you have to do is swap the radios. Now, again, I can sit here and tell you all day how to do it, but let me show you how quick it can go. From the C2 side of things, I just pull the dongle and I can just swap in a new dongle. Now from the implant side, I'm just going to swap the radio. All right. So now let's go ahead and jump back over to our C2. And we're just going to launch iHide again. We're going to choose our COM port. We're going to choose our baud rate. Now this time we're going to choose LoRa instead of Digi. Oh, I'm sorry. I got to get out of presenter mode. Thank you. All right, so here we are. If you look at the top, I chose option number 2 for LoRa over serial instead of Digi. And now I'm going to talk about a mode that we didn't mention before. Mode number 19, LoRa config. Who here has programmed with @ commands over serial before? Anybody? Yeah, so a few of you. I get really tired of memorizing my @ commands. So I figured I'm just going to build it in a C2 for you guys. So you don't have to worry about it. @ commands are used to configure hardware over serial communication. So like your ID for your radio, things like that. We're going to go ahead and choose option 1 because we're using the 998 radio. And now you can see we have all the options for configure. What I'm going to do is I'm going to choose option number 7 to check the ID. All right. So my C2 radio has an ID of 1. Now, if it was 0, that means it's a broadcast. So it will receive anything broadcast to 0 like every other radio. But for targeted as a C2, I don't want to be 0. I want to be 1. So I know my other radios too. Now, it gets embarrassing when I have them swapped. I'm like, hey guys, look, it works. And I have the wrong radio. So that's why I double check. Anyway, since we're on LoRa, let's go back, clear the screen, and now we are going to activate the implant. I could go through and do the full demo again, but it wouldn't be anything new for you guys to see. So I'm going to activate. I'm going to make sure I can talk to it. This time I'm going to talk to radio number 2. And now we're interacting over LoRa versus DigiMesh. So now we're working. Now, again, we could go through all the other commands, but can anybody tell me what that second file we left on the file system was? Yes, black cell txt. Let's go back and grab that file, shall we? We'll go option number 13. We want to go to radio number 2. C:users, self-aware victim, desktop, black cell txt. Oops. Give it a name. And now we're going to repeat the same process. Keystroke injection, creating the PowerShell session where we grab that file. We're going to gzip that file, base64 encode it, chunk it, send it back over, blah, 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 all the way back over to us. Now, on this side of the world, I'm going to give you a hash this time because I wanted to show something a little different just so you get the feel that I'm not just sending data over the same way it was. The file came in. Now let's go ahead and jump over to our directory. You can see we have OK. And now you can see we have what looks like an account number and a password. And for you movie buffs out there, if we know anything, it's that the password is swordfish, right? All right. All right, so that is LoRa, and that's how easy it is to swap the radios. But that's not the only technology we stopped at. We decided to take it a step further. And we thought, well, what else can we work with that's really popular at the moment? Well, we decided to jump on the flipper train. So I went through all the extensive hours and made a flipper board. I'm kidding, it didn't take me that long. What would have taken me a long time was writing the code, and I didn't have time for that, and thankfully, this is where Matthew stepped in.
All right, so while I'm setting this up, I have a question for the audience. How many of you have actually heard of the flipper before? I'm assuming, okay. Yeah, how many of you have actually developed a flipper app before? All right, that makes a lot of sense. Anyone who's done like embedded stuff or like Raspberry Pi, Arduino, that sort of stuff? Okay, so it's kind of similar. It's based off of, where's the other side? That's barely gonna fit in there. There we go. Okay, so it's based off of a system called FreeRTOS, which basically is just a real-time operating system, which basically is mostly used in like heart implants or like pacemakers or stuff like that, because you need something to happen at a very specific time and you need priority order stuff so that someone doesn't die, basically. But that's not that important for flipper development. What is, though, is it kind of changes the way you have to develop stuff. Is like mostly you're working with like event loops and threads that are working within those event loops. So that's kind of how you have to make your code if you're planning to do some stuff with flipper. But let's just quickly go through this. That's our splash screen for the app on the flipper. And you can configure your radio like you could before. You can go with different baud rates. I'm just having the default for what I'm doing here. You can also change XB or LoRa. And, oh, it's, okay. Yeah, that's, okay. Yeah, so I should go back. All right. So there's our splash screen I was talking about, and configuring the radio. You can get the different baud rates that I was talking about, different radio for LoRa or XB. I'm just going to do the XB with the normal baud rate. And then you have an about page, which is basically just GitHub links and stuff like that. But if you were using this, you'd connect to the implant and you hit the search page and you search, and it's going to search through all the stuff. It can potentially take up to 10 seconds because the radios have some sort of wait time so they don't all blast you at the exact same time. Implant is what we want to look into. So we click that. And this currently only has 2 things because 2 weeks before the presentation, I was getting a lot of crashes and it was very difficult to debug, mostly because I did not have the Flipper debug board. Lesson learned, I probably should have had that. The only other way I could do it was debugging it through logging, and it was not a fun experience, I would say. So lesson for you, if you guys are going to do a Flipper app, get that debug board and don't be like me. So we're just going to activate it to make sure it's ready to receive packets. And then we're going to sniff keystrokes, which is basically what John was showing before. So if could be good now. So if we go, hello there, General Kenobi, if you guys get the reference. But yeah, basically this is mostly to prove the point that you could get into a smaller form factor. Like this wouldn't have to be like a Flipper. It could be something like an Arduino. You could attach it there and have it like in your pocket going through something. Like I'm sure you guys can think of a bunch of different ways. Instead of lugging a laptop around, you can lug down something smaller like this and use it for something different than just waiting there. But with that, I'm going to turn it back over to John.
All right. Thank you, Matthew. All right. So that's not the only innovation we had. The next one was born out of me having to do a bunch of work. So I created a programming jig because those connectors that I was talking about that were hard to get, well, I didn't want those to hold things up, and I got tired of soldering them on for just a one-time programming. So we use pogo pins on this jig, and all you have to do is drop it on top of the JLC PCB board, screw it down, and now you have a programming interface you can use. So if you have 5 of these, 10 of these, whatever, it's going to go a lot faster. So that's what we were doing there. That's where we were. Where are we going? Well, let's talk other technologies, right? We have LoRa, we have Mesh. What about LoRa Mesh? Meshtastic sounds nice. So that's the latest radio technology we're looking at. What if you want to leverage the distance from LoRa, but the Digi XB mesh network? Well, let's make a gateway. So we can leverage that distance from the LoRa communication and then do mesh at the actual environment. We're looking at doing cellular C2 to gateway as well. NXP has a couple nice IoT radios we're looking at. And then when we started, we were talking about physical footprints, right? Well, we released the board design. Anybody can go ahead and get that, grab it with like JLC PCB, KiCad, and you can start manipulating what this board physically looks like. It doesn't have to be in line with the keyboard like we have designed. That was just the most convenient. We used it for 3D print cases. But you can start shaping the board to fit into things and fit your application better, because we already laid out the circuitry. You just have to move the components and change the shape of the board yourself. So use your imagination, how you want to do it. The code's open source, so you guys can change that as you want. So all of those things we wanted to change, we want to make sure we could give to you guys as well. So with that said, we're looking at other physical footprints just as a mock-up for people to use as well. With that, I'd like to give a special shout out to Jeremy Miller, the co-creator of Inject on Hide with me, the EFF for helping us disclose this responsibly, Soldier of Fortran and Redfish for their mentorship. If you're interested in learning more or contributing, you can scan that QR code. That'll get you there to our GitHub. That's where we have our C2, we have our documentation, we have video presentations, we have our Gerber files for the PCBs. all that fun stuff. You can find us on Twitter. I'm Camouflage. Inject on the Hide has its own page as well. We're on Discord. It can be quiet while we're working on things, but if it's quiet, I'm still monitoring it. Don't take that for a sign that we're not working, because we still are. And finally, if you don't remember all that, just go to injecto-hide.com and we'll redirect you to the GitHub as well. Any questions? Yes, I'm back. So the question is, has there been any testing in environments where they have additional controls in place like Avanti and stuff? I haven't run into any detections that have stopped me short of my payload. Now, I will say the original payload I had, the PowerShell one, I ran for 3 years before defenders started flagging on it. So as far as like AV and all that goes, we're connecting as a keyboard. Now we can change the vendor ID, the product ID, to mirror any keyboard that you would expect to attach. So we're really hard to catch from that standpoint, right? So your biggest risk of getting detected is in your payloads. Now keep in mind, we're going out that COM port too, so we're avoiding network detection. There is the ability for some EDRs to look down to the COM port level, but now you're talking death by logs, because that is so fine-grained. And to be looking for something at that level, I mean, not to say it can't be done, but whew, I don't envy that person. So any other questions? Yes. So the question is, would it be feasible to use this as a direct memory interface implant using the hardware? Not with the hardware I have right now, not with the SAMD chips. I'm using those chips because they emulate USB natively, so I don't have to add in additional modules, but I would redesign the board if I wanted to do that. Yes. We do that through Arduino, and I've tried, and I did it a while ago, but I believe it doesn't change. I know you can change. I was playing with the different vid-pid settings, but I do not believe I can change the serial number at this time. But speaking on new technologies, I've been reading up that they are now allowing dual boot for C as well as MicroPython, which has the ability to dynamically change those values. So I'm curious to see where that research is going to take us and what we can do with that. Great question. Anybody else? Yes. Oops. So we tried, the question is, do we have a way to keep people from hijacking the C2 side? So it's a defense in depth. So we have a join command like, Zigbee would, right? So we have an authentication and we have the encryption keys. Plus we have that special packet that we built in that you have to wake up the C2 to try to avoid, if all those failed, just replay attacks to get us to do something that wasn't intended. So you would have to be present at that initial command as well. Just because if people get lazy, right, and don't change these settings and leave it open. But we also, because we're the mesh, you have to be in the same physical vicinity to access that as well. So we talked about that, running 2.4s, that can be too noisy. Well, now you're just kind of hiding in the spectrum with everything else. Sub-gigahertz might be more covert. Nobody's war walking for it, but you're also going to stand out. So there's a lot of debate on like what the best way to stay covert and secure. But so that was the best we could come up with, was the encryption and the authentication plus the activation command to stay silent and then wake up. Any other questions? Nobody? All right. Well, if you do think of something, feel free to come find me. And with that, thank you for your time.